For today, we're going to be looking at characteristics of polynomials. All right, we're going to be looking at three main things: maxima, minima, and extrema. I'm going to explain what all these things are and how to find them on a graph or whatever you might be given. All right, first we're going to look at is maxima. All right, there are two types. There's an absolute maximum and a relative maximum. All right, let's look at the absolute first. So it is the tallest or the highest possible point on the graph. Now there are limitations to what a maximum can be, okay? And we're going to show you that when we get to the graphing part of this. So just keep that in mind, the highest possible point, okay? Versus a relative maximum is just a highest point, or not highest, a high point on the graph. Right? When I think of maximums, I think of peaks. Think of like mountain peaks. Okay? Let's look at a graph example. Let's look at two of them, okay? So I'm going to make the graphs part big. Okay, here's my second graph I'm going to make. Okay. Let's look at what is a maximum and a relative, or an absolute maximum and a relative maximum. Okay, right here I'm going to make this different colors. We have a maximum. It's the highest point on a graph, but it's only a relative. And the reason it's only a relative, you might think, well, that's the highest point, but this arrow here is going up towards infinity, and that's a highest point. But we can't ever get to that point because we can't actually touch infinity. So this is only a relative maximum, okay? And the next graph, this is the very highest point the graph is ever going to go, because if you look at the two arrows, they're both going down. So this would be an absolute maximum. All right, it is also a relative maximum. Okay, so this is an absolute maximum. Oops. This is an absolute maximum. I get it. There we go. All right. Well, we have two relative maximums. Okay, I'm going to make those two different colors, actually. We have a relative maximum here, and we're going to do this one as well. Okay, those are both relative maximums. It's just that one of them is an absolute max as well. Okay, because now nothing else can be higher than that one point. All right. Versus the other one, there is something higher than the point, so it must be only relative. Okay, so any peak is going to be a maximum. It's just, is it the highest possible point on the graph? All right, and in the first graph that we showed you, there was something else that was higher, but it just keeps going. On the second graph, there is no other point on the graph that's going to be higher than that absolute maximum. Okay. All right, now let's go to minimums. Change my color here. All right, absolute minimum is the lowest possible point. On a graph. Okay, so there's nothing lower than that. Okay. A relative minimum is a low point on the graph. Okay, when I think of minimums, I think of valleys. Okay, so peaks and valleys. So let's do a little bit of a same thing that we just did. Hold on. So we have our graph and our second graph. This time we're going to do it a little bit different. Okay. So let's check out what a max and min would be, or sorry, a minimum would be. So this is a relative minimum because although it is the lowest point on the graph, that arrow keeps going down towards negative infinity, so there's lower parts, so this must be only a relative minimum. Okay, all right, so now it also has a relative maximum, but we're not talking about those right now. All right, on the second graph, this is an absolute max, or absolute min, sorry. All right, there's no other point on this graph that's lower than that spot. Okay, and notice these are all the values, the low spots. Okay, this graph also has two relative minimums, here and here. Okay, those are both minimums. One of them is an absolute minimum, but they are both relative minimums. Okay, so you hopefully you kind of see the connection between relative mins and relative maxes, absolute mins, absolute maxes. Absolutes have to be nothing else can be below them or above them. Okay, relatives can have just be a peak or valley in the graph. All right. Lastly is extrema. All right. Extrema is, I'm going to try and make this a little bit easier to understand. Extrema is just all peaks and valleys. I'm going to change this color. All peaks and valleys. In a graph. Okay. So, now the number of extrema that you have in a graph is related to the degree of the graph. We've already seen this in the number of roots you can have with a degree of a graph. Okay, in the last unit. Was it the last unit? Yes. Or was it this unit? I don't remember. Either way. Okay, so let's look at a fourth degree polynomial extrema. Okay. Fourth degree. So that means x to the fourth. Okay, so you could do a couple different things that have x to the fourth degrees. This is one example. Here's another example. Okay, now let's look at the extrema, the relative mins and maxes as a grand total. All right, when we look at the extrema, do red. All right, we have one absolute absolute minimum. It's the lowest point on the graph. One absolute minimum. Here we have 1, 2, 3 extrema. So these are all the peaks and the valleys. So there's one peak and two valleys in the second graph. So there's 3 extrema. And the first one, there's only one because there's only one valley. There are no peaks. Okay. After this, you'll notice our x to the fourth. In the second graph, I have, let's highlight it. I know I can't go any more than this because I have 1, 2, 3, 4 different roots, and that matches our degrees, so I can't do more stuff, because any more stuff, then it's not a fourth degree polynomial. Okay, let's look at a fifth degree. I might have to get a little bit smaller in my graphs so I don't run out of space. All right, so I'm going to make this bigger so it's easier. Fifth degree. Nope, hold on. Yep. There we go. All right. So if we count these up, you could have, there are no extremas here, okay? So there's none. Because there's no peak or valley, just a flowing curve. Here, so we're going to put 0. Here there are 2. Here there are 1, 2, 3, 4. Okay? Hopefully you're seeing some kind of pattern as we move through these. We'll do the last one is 6th degree. So here you're going to have this way. Okay, again, you'll notice that on the last graph I did, there's 1, 2, 3, 4, 5, 6 different solutions or zeros that matches the 6th degree polynomial. If we look at the number of extrema, we have 1, and we have 3, and then we have 1, 2, 3, 4, and 5. Okay, so we could keep going to bigger and bigger degrees, polynomial degrees, all right? But this chart on the bottom kind of also shows you the different functions you can have and then different extrema you can have, all right? So the big question is, how many extrema and what is the pattern? So what I'd like you to do is take a moment, pause the video, do these next 3 things, write them down so we can see them, and then unpause the video, and then we'll go through them real quick. All right, so pause the video, do these, the 4th, 5th, and 6th degrees, right at the extrema you can find down when you circle them, and then we'll come back. All right, so hopefully you're back. You've tried this out. You can come up with what your answers were. So we have 1 extrema there, 1, 2, 3 here. In 5th degree, we have, well, there are none. Then you have 1 and 2. The last one you have 1, 2, 3, 4. All right, and then 6th degree, you have 1, 1, 2, 3, then 1. Let's make this bigger so we can see it. 2, 3, 4, and 5. I know those are small, but they are there. So the question becomes, what do you notice about the possible number of extrema and the degree of a polynomial? Okay, well, there is a pattern here, okay? All right, you take the degree number minus 1. That is the most number of extrema a graph can have. Okay, so you'll notice with 6th degree polynomial, you had 5, all right, and then you go every other 2. Until you get past 0. All right, you can't go less than 0. You can't have negative 1 extrema. So that's what it is. So there is a pattern here. Okay. So let's show you what the pattern looks like just theoretically here. So you're a 9th degree polynomial. And that means you can have, if we take 9 minus 1, we get 8. And it's every other 2 going down. So it's going to be 6, 4, 2, and 0. That's how many extrema you could possibly have in a 9th degree polynomial. Okay. Now, when we're graphing a 9th degree polynomial, we're going to go through the x-intercept. We can go up to at least 9 times. So let's try that. Let's see what it looks like. So 1, 2, 3, 4, 5, 6, 7, 8, 9. There we go. There's a 9th degree polynomial. All right, that has 8 extrema. If we had less roots, times where it goes through the x-axis, we would have less extrema. Okay. For a 12th degree polynomial, you take 12 minus 1 gives you 11. Then every other number going down, which gives you 9, 7, 5, 3, and 1. Okay, we can't go past 0, so we're done after 1. Okay, now I'm not going to go through 12 times. We could, but we just need to have an odd degree number of extrema. Or an odd number of extrema, sorry, not degree. So here's 1, 2, 3, 4, 5. There we go. That could be a 12th degree polynomial. It's got the right number of extrema. No, wait, hold on. No, it doesn't. 1, 2, 3, 4. I missed one. 1, 2, 3, 4, 5. There we go. There we go. Now we're on set. So you got 1, 2, 3, 4, and 5 number of extrema. Okay. The reason I knew that other one was wrong is because it was an even degree. That means it has to start and end in the same direction. So good key thing to think about there. As with the 9th, since it's an odd, they start and end in different directions. So I know that one was okay. Okay, so that's the pattern you get for extrema. So let's try it in this way. So an 8th degree polynomial, what is the number of possible extrema you can have in an 8th degree? Okay, so we take 8 minus 1 is 7, and then every other number going down. 5, 3, 1. All right, a quartic function is an x to the 5th. If you take 5 minus 1 is 4, 2, and then 0. 13th degree, 13 minus 1 is 12, then every other number. 10, 8, 6, 4, 2, 0. And then 7th degree, you have 7 minus 1 is 6, 4, 2, 0. Okay, so all the odd degrees are going to have even numbers for extrema. All the even degrees are going to have odd numbers for extrema. Okay, so here we go. Match each graph with the description to the right. So take a moment, match these up, pause the video, and then come back. All right, so hopefully you're back. We're ready to see how you did. So let's go through these one at a time. Number 1 says even degree with 2 roots. So even degree means that it has to go, it has to start and end in the same direction. If there's 2 roots, well, there's only 2 that are even degrees. It's A and C, because they both start and end in the same direction. With the 2 roots, this has to be A. So this is number 1. All right, a cubic function with 2 extrema. So a cubic function is an odd degree. All right, 2 extrema means it has to have, there's only 2 that are odd degrees. It's B and D. Let's erase this. Okay, and the the number 2 extremas is going to be these 2. So this is going to be number 2. This is B. A quartic function with 3 roots. Oh. You know what? I might have made a mistake up at B. Quartic is actually x to the 4th. Let's take a pause real quick. This should have been x to the 4th. I misread that. Quintic is x to the 5th. It's very close. So if it was x to the 4th, it would have been 3, 1, and that's it. Okay, sorry about that. Back here, quintic function with 3 roots. It's going to be C. They're going to go in order, I'm sure. Look at this. The last one's going to be D. Cubic function with no extrema. There's no extrema in graph D. All right. Look at this one. Multiple choice. Which graph below could represent a cubic function with exactly 3 zeros? Okay. So cubic function means it's x to the 3rd. We're looking for an odd degree. All right, which means that it has start and end in different directions. Well, that cancels out letter A because it starts and ends both going down. 3 zeros, here's 1, 2, and 3, so it's going to be B, because C only has 1 0. Here's the last question of our notes. We have 2 different functions. We want to figure out which one has a greater relative minimum. Okay, so the highest and minimum that we can get. Okay, so we can see the relative minimum for this first graph is right here. Okay, so now what we're going to do is we want to do a quantic. Notice quartic versus quantic. There we go. Quantic function with 5 distinct real roots. Okay, notice this piece, A is greater than 0. That means the first term, the x to the 5th, is positive. Because it says that the A value is greater than 0. Okay, so if it's a positive function and it's x to the 5th, your graph's going to look like this. It's going to start up at the negative part because it's a positive function. All right, and we have to have 5 distinct roots. So there's 1, 2, 3, 4, 5. All right, so because it has 5 distinct real roots, we had to go through the x-axis 5 different times, which means all of our relative minimums are below the x-axis. That means the graph here, f of x, has a higher, greater relative minimum. So I'm going to write that down here. So f of x has a greater relative minimum because g of x minimums that's ugly. I spelled minimums wrong. Are below the x-axis. Okay. All right, that is it for the notes for the characteristics of polynomials. All right, please make sure you try out the practice. All right, refer back to the notes if you need to, and good luck.